Here we are in section 19.5, working our way through. I thought I would use the color green so we could go. Very, very bad pun. Anyway, why is this called Gibbs free energy? Why does it get the letter G? Well, Gibbs was the first American to earn a PhD, and he earned it at Yale. And what he did is he applied thermodynamics, and when he did that, he transformed what was really physical chemistry into a rigorous inductive science, best left for an upper level course. What do we want to do in this section for us in Chemistry 1220? Well, we want to imagine that a rock is sitting on the top of a hill and it starts to roll downhill. So I think everyone watching this would say it will stop once it reaches what's called a valley. Well, that's the analogy we want to make for Gibbs free energy. Gravity drives the boulder until it reaches a state of minimum potential energy in the valley. What I did in the next slide is I put one picture next to the other. I'll go there first. Here we have the reactants. Here we have the products, and in the middle, we have the equilibrium mixture. So that's how you should think of this. Depending whether you have reactants to products or products to reactants, it will always go and find that minimum potential energy. And we have now put a G on this axis, and we've put a new thing called course of reaction running across the bottom. So where does all this come from? Gibbs is the one who proposed that G is equal to enthalpy minus T times entropy. I honestly don't know where that comes from, but that doesn't make any difference. We are going to be using standard conditions. Notice the little zeros that are these superscripts. They designate standard conditions. What we want to say as we start this section is, if delta G is negative, the forward reaction is spontaneous. Think of the egg drop, how it dropped. If G is positive, the reverse reaction is spontaneous. I know it's weird to think about that, but it'll make more sense as we go deeper into the chapter. And if delta G is 0, the reaction is at equilibrium. And very soon, as we move through the chapter, we'll be pulling in the equilibrium constant. So what's the take home from this slide? The picture. Think about the boulder analogy. Think about every reaction going to equilibrium and know that we can describe it using that Gibbs equation. This is kind of like a curveball whenever I have to teach this. They put in the Q. And if you recall, the Q back in chapter 15 was really any concentration, and you would try to figure out if Q was greater than K, less than K, which way the reaction would shift before equilibrium. If you think about that before you look at this picture, it makes a lot of sense. Here is our reactants, nitrogen and hydrogen. Here is our product, ammonia. We know they are going to eventually reach equilibrium in the course of the reaction. If we start with reactants, we see that it is spontaneous in the forward direction towards equilibrium. Well, think about the first item we have here. Q is less than K. Back in chapter 15, we would draw an arrow that would take us to what the shift would be. We would say shift to the right. And what they say in this section is, it is spontaneous in the forward direction. You already know about the right shift. All you're adding to your vocabulary is spontaneous in the forward direction. Think about the second one they have here, where Q is equal to K. Take a look at the picture. That is in the energy well, and that is what we call equilibrium. Now, I don't think it's going to take a mental giant to figure out the next one, but look where that arrow is. It has its point there, and you would have told me in chapter 15 that you were going to shift to the left. So what does it say in this section? It says spontaneous in the reverse direction. So It should make some sense based on calculations we did in the past when we looked at actual numbers, when we compared Q is equal to K or Q versus K. We would say the shift will occur in a specific direction until it reaches equilibrium. That's essentially what this picture is. You will absolutely never have to reproduce this picture. But if you see the picture, you would need to label it. You would need to know what does it mean. Okay, so that's really the concept. Now we've got to actually talk about delta G of formation. We assumed in that equation that, we knew what it meant. But what is a standard free energy of formation? The little 0 tells us it's a standard. The F tells us it's a formation, and it has a value of, it's the standard free energy at 25 degrees centigrade. That's why I left a blank. And you can now laugh because what it should say here is and a blank, but it tells you what atmosphere. A little bit of a bonus just to keep us all awake. So just like with delta H, a standard substances are pure solids. They are pure liquids, and if you have a gas, it is 1 atmosphere. If you have a substance in solution, those are all the standard states. They have all been tabulated, or they will be provided to you, and elements in their standard state have a delta G0 formation equal to 0, okay? So again, it parallels delta H exactly. The nice thing is, when you do a calculation, you will have one just like you had before. It will be Hess's law. So these are all the attributes we can attribute to the standard energy of formation. All you're doing is expanding your repertoire. You're just substituting a G for an H. Two kinds of calculations. I did the first one using the delta G equation, where we would have delta H Z over reaction is delta H0 of the reaction minus T delta S0 of reaction. You would be given these two values, and since it is at 0, we would, it's a formation, we would know that it is 25 degrees centigrade. So once again, we're just going to put our numbers in. 180.7 kilojoules. Now here's where it becomes, and I'd often say in class, what do we need to do? Well, we can't use 25. We need to use 298 Kelvin because the temperature must be in Kelvin. And in terms of the S we use, we have to use it in terms of kilojoules because that's what we've put delta H in. So we would multiply it by 0.247 kilojoules per Kelvin. And when I crunch my numbers out, I would get 180.7 kilojoules minus a tiny number, 7.36 kilojoules, giving me a delta G of reaction of 173.3 kilojoules. Now this is a positive number. This says that this reaction is not spontaneous as written under standard conditions. So again, lots of language, but the main issue is not spontaneous at 298 Kelvin. Sometimes you will be using this Gibbs equation. Other times, you might be given the values of delta G0. And I wanted to do that for you so that you could see what's going on. Just like delta H, free elements or diatomic materials have a 0. Oxygen has a 0. And you would look up the value for nitrogen monoxide, and you would find an 86.71. These are all in kilojoules per mole. And here is where you would use Hess's law. You would say delta G0 of reaction is the sum of the delta G0 of the products minus the sum of the delta G0 of the reactants. All you would do is put the numbers in. Did I say the word easy points? 2 times 86.71, those are your products, and your reactants, oh, that's a gift. So essentially what you get is a value of 173.1 kilojoules per mole. Now, if you look back at the slide previously, we got the number 173.3 kilojoules per mole. They are close enough. Depending upon how you calculate, your last digit may be different. But what it does do is delta G0 is a positive. This reaction is non-spontaneous in the forward direction. That's really the take-home message. This whole section wants you to realize, what does the sign in front of delta G tell you? How does it relate to a Q? And backing up either further, what does that have in terms of a concept? Think of the rock rolling downhill. Again, please do the homework problems, especially the sample exercises, because they are the ones that are going to make you think. I will be adding a little video once I get some feedback from people about questions they have about these sections, just as if we were in office hours.